So we left off speaking about the balance of energy, this post-absorptive versus absorptive state, which I was referring to as the fed versus the fasted state, okay, or the fed and fasted state. So we left off speaking about, I believe it was insulin. And so I can't quite remember where. So we'll just kind of pick back up with insulin and then we'll move on to glucagon. I think we left off here. So we were speaking about the role of insulin here. And insulin we mentioned was an anabolic hormone. So it is going to decrease catabolism, but it's going to be responsible for anabolic events in the body. That is the building up of things, right? The building up of triglycerides and fatty acids, the building up of proteins, the building up of glucose into glycogen. And so it's going to be secreted during the absorptive state, right? Think about having a large meal, really make sure you're bringing the practical application to this. So you've had a large meal, you're well fed, you're gonna have a lot of insulin being secreted into your bloodstream. That is going to help increase glucose in the plasma. That's going to be another stimulus, sorry. So increased glucose in the plasma is another stimulus for insulin secretion so that that insulin can be uptaken into the cells to be used. Increased amino acids is another one of those plasma triggers or sensors or stimuli for insulin secretion. If we had a large meal, we're going to have these types of things in the plasma, amino acids, glucose, and the reaction is for them to be uptaken to either be used appropriately or to be stored if they are needed. The parasympathetic system and GIP are two other stimuli. Again, parasympathetic, we're thinking rest, digest, so that will definitely be a trigger for insulin release. And then GIP is going to be secreted in response to glucose coming into the stomach, but also the stretch of the stomach. We kind of talked about this before, and that would be another trigger for insulin to be released so that we can start building up those nutrients, storing away where needed, and using them in the cells, such as the brain and general cells in the body to release energy. Now, insulin secretion is going to be decreased in the post-absorptive state, right? So if you're in a fasted state, you've gone maybe a couple hours without a meal, you're going to have low levels of insulin. Other stimuli for this are going to be the sympathetic nervous system. So if you just ran a marathon, if you're scared, nervous, you have that fight or flight response going on, you're going to see lower levels of insulin secretion as well. All right. Okay, just reiterating that here in this schematic, right, kind of illustrating that. So our beta cells are the cells, right, the centrally located cells of the islets of Langerhans, which is the endocrine part of the pancreas that secrete this insulin. So if we have a large meal, we have lots of insulin being secreted, these are the four types of responses that we're going to see. In our genital tissues, we're going to see that glucose being uptaken. So this is going to be used immediately as needed for energy. So muscle cells, liver cells, brain cells. We talked about this idea that the brain really prefers exclusively glucose. And so it's going to really grab for that glucose as it is being released immediately from that large meal. Other things that we're going to see are amino acid uptake to kind of store that away as proteins. Protein synthesis because of that amino acid uptake, and then a decrease in protein breakdown because we're trying to build things up for later use and prevent the breakdown because we're obviously having enough of those coming in through those sources in the diet, immediately that is. In the adipose tissue or fat cells, we're going to see a buildup of fatty acids and triglyceride. We're going to see a decrease in lipolysis. So we're going to see a decrease in the amount of fats that are being broken down. Again, we're turning off catabolic events and turning on anabolic events. In liver and muscle, we're going to see an increase in glycogen synthesis, kind of storing that glucose away in glycogen. And then we're going to see a decrease in the breakdown of that glycogen, which is glycogenolysis. In liver cells, we're also going to see that anabolic event of increased fatty acid synthesis, increased triglyceride synthesis, and decrease in the catabolic event, which is that gluconeogenesis. And gluconeogenesis is synthesizing new glucose from other sources, right? That genesis here means the new creation of, and gluco meaning glucose. So we can take things like fats, to some extent proteins, and we could use those to synthesize new glucose. All right, so moving on, kind of shifting gears here, the opposite end of the spectrum is glucagon. So glucagon is the antagonistic, sort of the evil twin brother of insulin, and it has the opposite set of effects or events. It is secreted from the alpha cells of the islets of Langerhans. So these are the more peripherally located cells. So just to review this is our pancreas. It's got a mixture of cell types here. We've got the exocrine gland portion, which is the yellow portion, that is secreting pancreatic juice, pancreatic enzymes, that is going to be secreting into the ducts, hence the term exocrine. Whereas the green part is the endocrine part of the pancreas, which is the islets of Langerhans. And that is going to be secreting or releasing its secretions into the blood, hence the term endocrine part of the pancreas, right? Now, within the islets, we talk about several different clusters of cells. The more peripherally located cells were the alpha and delta cells. Specifically, the alpha cells secrete glucagon. And glucagon is going to be promoting glucose sparing, especially for the nervous system. So it's going to kind of preserve or reserve most of that glucose coming in for the brain. The brain prefers glucose. It's also going to help mobilize energy stores. So it's a catabolic hormone, right? It's going to help with glycogenolysis, breaking down glycogen to liberate glucose from liver and muscle. It's going to help with lipolysis from our fat cells, breaking down those fat cells to liberate fatty acids. It's also going to help with gluconeogenesis, again, seeking other sources that we can find as substrates to make new glucose. All right. And so in that way, it will be a catabolic hormone, so liberating energy, and it's going to decrease anabolic events, which we saw with insulin. The triggers for glucagon secretion are going to be the post-absorptive state. So that is sympathetic nervous system, fight or flight, whereas the antagonistic function, so things that will decrease glucagon secretion, are going to be absorptive state, which is going to be excess amount of glucose in the plasma. The parasympathetic system is another thing that decreases glucagon secretion. And so this is how they are sort of antagonistic, right? Glucagon and insulin having that antagonistic function. So if you're in a fight or flight state, you're going to increase your glucagon secretion, but you're going to decrease your insulin secretion and vice versa. All right, just kind of illustrating that here as well. The alpha cells secreting glucagon. So this is if you've gone maybe a couple of days or a couple of hours without a meal, you have lots of glucagon being secreted into your bloodstream, and glucagon is going to be bringing about these sets of events. So from the liver, it's going to turn on or increase those catabolic events. It's going to increase glycogenolysis, breaking down glycogen to make new glucose. It's going to increase gluconeogenesis, the synthesis of new glucose from other substrates. It's going to increase protein breakdown to liberate amino acids, right? It's then going to decrease the anabolic events. So it's going to decrease glycogen synthesis. It's going to decrease protein synthesis, which is basically shutting down those more anabolic events. Okay, and then ketone synthesis is another one that's going to increase. This is a catabolic event. This is where we can use beta oxidation to break down fats to liberate energy as well. And then as far as our adipose tissue, it's going to help with lipolysis, so being able to tap into those fat stores, break them down to liberate fatty acids and glycerol to be used as energy. But then it's going to turn down or turn off the anabolic events, which are triglyceride synthesis. Okay. All right. And then just comparing the actions of insulin and glucagon to talk about how we regulate blood glucose levels. So our normal blood glucose is anywhere from 70 to 110 milligrams per deciliter. If we go above 110, we're getting into pre-diabetes range. If we go above 126, we're definitely into the diabetic range. And if we have hyperglycemia, this is 140, right? So anything above 140 is hyperglycemia. Anything below 60 is hypoglycemia, right? And so insulin and glucagon are working hand in hand to maintain our normal blood glucose levels. This is what we need insulin for. When we have a large meal, we've got lots of glucose in the blood, right? If we have a large meal, our blood glucose level can go as high as 140 or above. And so that glucose needs to be moved into the tissues where it can be used to liberate energy. And so you may not be diabetic. You can still have these high glucose levels if you just had a large meal, right? That is normal. But when we talk about the diabetic range, that is going to be fasting glucose. So if you wake up early in the morning and you've had no ingestion of food, you have no glucose in your system, your blood glucose level should not be above 126, right? So that's where we get into that diabetic definition. But if you just had a large meal, it's perfectly normal to have hyperglycemia, which is higher glucose levels after eating. And so what that is a stimulus for is insulin secretion, so that we can move that glucose into our cells so that it can be used, and we can help to store up that glucose via the mechanism that we described for later use. That's those sort of anabolic events, like the storing up of triglycerides, storing up of proteins, et cetera, for later use.